So far we covered two solving methods for the simple problems. One of them was the intuitive one, the second was a graphical approach. The third one we will cover is that by enumerating the corner points. That means that we have to find every corner points of the solution and find the objective function values and choose the one that has a higher objective value function for the maximization problem and minimum objective function for the minimization problem. In this figure you can see that for each corner points, we have the objective function. For example, for 0, 0, when we do not produce anything, we get the objective function equal to 0. And then as we discussed in the intuitive method, if we do not produce any x1, any x2, we can produce 174 from product 1, and our objective function or our profit would be $60,900. Similarly, if we do not produce any product from product 1, we can produce 180 from second product and our profit is 54,000. And if we produce 122 from the first one and 78 from the second product, we get $66,100, which is best objective function across all the possible points. This is the highest value, so this is the optimal solution of the problem. The most important thing in this problem is that how to find the corner points. For example, as we discussed, this is we assumed x2 is 0 and we find x1. But in a systematic way, when we have 3 constraints and 2 sign constraint, lower bound of the constraint, we have to get the intersection of each 2 constraints. That is, when we assume, let's say, x for this particular point, we assume x2 is 0, so this constraint gone, and we find one of the intersection of the one of this constraint which has the smallest value, which is intersection of the constraint third constraint and x1. In general case, we have to have intersection of the each 2 constraint when we are working in the 2-dimensional space, when x1 and x2. So for example, we have to have a intersection of the 1 and 2, the constraint 1 and 2, constraints 2 and 3, and constraints 1 and 3 to find every possible corner points like this or like this. And then each of the constraints and boundaries, x1 greater than and x2 equal to 0, and 2 second constraint, and x1 is positive and x2 is 0, and other. Also we have to consider first constraint and x2 positive and x1 is 0. Once we have all of these points, we have to check the feasibility of the points. That means when we got these points, we have to put in all 3 constraints, and see whether they are satisfying the constraints or not. So the corner point, then in the enumerating the corner points, we have to have intersection of the constraints and make sure that the solution we got from the intersection of each pair of the constraints are feasible and they are not violating any of the constraints. So far we investigate one problem. Now we want to see what will happen if we change any of the parameters, including the coefficient of the problem we investigated. You can download this file from the web page of the course, which shows the problem we investigated so far. You know, the objective function of the problem, you know, 350 profit of the producing first product and 300 profit of the producing the second product. So this shows the objective function, and this is a total profit, which is multiply 350 by this number plus multiply this number by this number and add them up. So this is the total profit. And this is the first constraint, which is the pumps, and this is the second constraint, shows the labor, and the third constraint is the tubing constraint. And this is the right hand side, we had it before. This green point shows the optimal point, as we found before, and this blue lines is the level curve at the optimal level, and the other line shows the constraint of the problem. Now we want to investigate effect of the changing each of these parameters on the optimal point of the solution. Let's increase the profit of the first product from 350 to 450 and see what will happen. You see, as I increase the profit level, the slope of the profit level line is changing. Notice, you know, from 2 it has increased by this much, and then when I increase it by 450, the optimal points becomes all of these points. All of these green points are the optimal points, and this is one possible case that we will investigate later on. So this is one effect. By increasing the coefficient of the objective function from 350 to 450, we found another optimal solution, and the number of the optimal solution is, in this case, is a lot more than the previous case. In this point, every points on this line, on this green points, all of them are optimal points. So we have a lot of options here. Now let's change another parameter in this problem. Let's increase profit of the second product from 300 to 350. As you see, again, the slope of the level curve is changing, and now by increasing the profit of the second product from $300 to $350 per each product, we found another set of the optimal solution. In this case also we have a multiple optimal solution. Similarly, you know, the level curve, if you notice, the level curve is exactly same as one of the constraint here. And then if we look at another problem we just investigated, that is, if we change the profit of the first product to 450, you can see the blue line is exactly equal to one of the constraints we had already in the system. So in this case, if the objective function is parallel to one of the constraints, then we may have a multiple optimal solution. So let's start again. Let's change one of the parameters. Let's change another parameter of the problem. Let's say each product, the number of the pumps available is, let's make it more 400 instead of the 200. The constraint associated with number of the pumps jumps up to here, and then this constraint is not setting any restriction on the feasible area. You know, the feasible area is generated by the first and the third constraint. You know, this this line, the orange line, is third constraint, and this red line is the shows the second constraint. So the first constraint, which is shown by this line, the red line, is not effective anymore. We call this one redundant constraint because it doesn't have any effect on the feasible region. And then you see that we have optimal point here, and the value of the optimal point, you can see, is 108 from the first product and 99 from the second product. And this is the value of the optimal profit we have. Now let's change another parameter and see effect of the changing the parameter. Let's say the first product needs two pumps, and the first one needs second product. The second product needs just one product. Then you can see the feasible region has changed. The feasible points have changed, and you can see the second constraint, which is shown by this line, is redundant. It doesn't have any effect on the feasible solutions. So an optimal solution is right here. So far we have investigated two cases that one of them we may have multiple optimal solution. In another case we may have a redundant constraint. There is one more situation that we may have case that we don't have any solution for problem. So based on our discussion, we can have several special conditions in the linear programming model. One of them is that we can have alternative optimal solution, redundant constraints, unbounded solutions, and infeasibility. We discussed alternative optimal solution and redundant constraints. So we have discussed these two, but we haven't seen these two cases. We are gonna see in a moment, but let's talk about alternative optimal solution. Let's change, as we did already, we change the profit of the first product from 350 to 450 and see the effect of this change. Let's again open the Excel file that we have and see the effect of the change. So we are changing 350, the profit of the first product, to 450 and see the effect of change. Again, as we did before, we can see that these green lines are optimal solution of the problem, and we have multiple optimal solution for this problem. We already discussed this case. So by changing this 350 to 450, we change the feasible area, and the level curves becomes parallel to the one of the constraint of the problem, and then we have multiple optimal solution, or we can say alternative optimal solution. Note that any point on this line is optimal solution of the problem, and we can choose any of these points. These points and these points are optimal, and any combination of these 2 points are optimal solution of the problem, and they will have a same equal optimal profit. Now we discuss another possible scenario, which we have a redundant constraint. The redundant constraints mean that a constraint that does not have any effect on the feasible region of the problem. Now suppose we change the first constraint, the right hand of the first constraint, from 200 to 225, and see what is the effect of this change. Again, we open the Excel file that we have, and we changed 200 to 225 and see the effect of change right now. And then you can see the first constraint has moved up a little bit, and it does not impose any restriction on the feasible area, and the green line the green point is our optimal solution, and this line, the red line, does not have any effect on the feasible region. So we call this one as a redundant constraint. This shows the figure we just already discussed. By changing the right hand side of the first constraint from 200 to 225, the first constraint becomes redundant. Now there is one more situation that we may have unbounded solution. That means that we have plenty of the resources from one or two of the decision variables, and we can increase it by infinity. We can increase it as much as we want, and we have a lot of resource from that one. Let's consider a problem with two decision variables, x1 and x2, and we have two constraints and two sign constraints. x1 plus x2 is greater than 400, minus x1 plus x2 is less than 100. So the first constraint is plotted here, right there. You can see this is the first constraint, and if we put 0, 0 in this case, in this constraint, 0 is not greater than 400. So this constraint is this way. The points in this area are the feasible point for this constraint. And then it says minus, the second constraint says minus x1 plus x2 is less than 400. And this is the line we have, the second constraint. Let's put 0 and 0, and you see 0 plus 0 is less than 400. So the feasible points are this area, and the union of these two constraints shows this one as a feasible area, feasible region. Now we can show the level curves, and then let's say we put x1 plus x2 as an objective function equal to 600, and then the way we found the level curves is that we put one of them equal to 0, and then we find another one. If we put x1 equal to 0, x2 becomes 600, and similarly if we put x2 equal to 0, x1 becomes equal to 600. And then I can connect these 2 points that we get from this solving equation. So 0 and 600, and 600 and 0. So this is one level curve, and the level curve, the value of this level curve is 600. And you can see that I can increase this line by any value that I want. I can increase it by 800, 1000, and so far. So I can increase it as much as I want. There is no constraint on this solution. So in this case, because there is no constraint that limits increasing the level curve, we say this problem is unbounded. The value of the objective function can go to infinity. Also, we have another possible scenario that we do not have any feasible area. In this case, we call it infeasibility. It means that the constraints are in such a way that we don't have any points that satisfy all the constraints. Let's have an example. Let's say we have objective function which is maximization of x1 plus x2, and the constraint is x1 plus x2 is less than or equal to 150, and the second constraint is x1 plus x2 greater than or equal to 200. So let's plot the first constraint. x1, you can put 0 as a x1 and you can get 150, and you can put 0 for the second for x2 and get 150. If we connect these two lines, 2 points, we get this line, right? And then if we put 0, 0, we can see that satisfies this constraint. So the area for this constraint is this area. Now for the second constraint, if we put x1 equal to 0, we get 200 for this one, and if we put 0 for the x2, we get 200 for the x1. And then if we plot these 2 points, we get this constraint. And if I put 0, 0 to find the area that shows this is shown by this constraint, I can see that 0, 0 does not satisfy this constraint. So it means that this constraint is showing this area. And you can see there is no intersection, there is no common places, common region that covered by these 2 constraints. So the feasible area is empty. We don't have any feasible area defined by this constraint. So in this case, we say the problem is infeasible. There is no solution for this problem. The constraints are contradicting each other, and we don't have any feasible area for this problem.